Hi there, my name's Chris Collison, and we're carrying on now into week 3 of Quantum Mechanics and Chemistry, CHMP 442 at RIT. And this week we're going to start to think about a particle in a three-dimensional box and degeneracy. We'll think about using quantum mechanics to determine the average or the expectation values. And then in the remainder of this week, we're going to start to look at the quantum mechanical postulates that we're going to find in chapter 4 of Quantum Chemistry by Donald Macquarie. So thanks for watching, and good luck with the quantum mechanics this week. So before we get started, let me give you a quick recap of week 2, this being week 3 and this being lecture 9. So in week 2, we introduced the rules of quantum mechanics, and those 5 rules are listed below in here. So we describe the system with a classical physics description. We insert quantum mechanical operators, and these operators are linear, and they may be commutative or non-commutative depending on our need for addressing the Heisenberg uncertainty principle. We plug the operators that went into our classical description. We plug that set of operators into our Schrödinger equation, which is an eigenvalue problem, which we then go on to solve in our 4th rule. And then we looked very recently at applying boundary conditions and normalizing. We spent some time on those considerations in the last lecture. We've also thought about probability and normalization. This, of course, comes up in Math Chapter B in the textbook. And we started to illustrate how we apply these boundary conditions by using a particle in a box illustration. So what are we going to do today? So I'm going to introduce to you the three-dimensional particle in a box, and then we'll go on to think about something called degeneracy, where many different states can have the same energy level. I'll talk to you about average values, which will come up later as a postulate in chapter 4. And one of the key takeaways at the end of the first lecture this week is that the Hamiltonian operator is separable. So we'll think about the method of separation of variables and how that can be useful. In the next lecture, that will be lecture 10. So that will start to talk about things that are coming up in chapter 4, the quantum mechanical postulates 1 to 5. So we'll talk about well-behaved functions. Again, we'll talk about linear operators for each observable. We'll talk about the only values that are ever observed in a system that is small enough to require quantum mechanics. The only values that are observed are those eigenvalues. We'll talk again about average values, tying a few things together, and I'll also introduce to you the time-dependent Schrödinger equation. Okay, so with that said, let's kick on with today's lecture 9, which will cover the first few parts of the description. Thanks for listening. So first off, today we're going to review what's actually in Macquarie's textbook section 3.7, and we are going to look at the statement: we can calculate averages for various physical quantities such as position and momentum. And so let's put this into perspective. Suppose we wanted to know the average position of the particle of interest over a certain range. So how would we calculate it? Well, we would calculate it as follows. We're going to introduce an expression here. We're going to use these brackets around the x in here. This is going to mean something called the expectation value, or the average. And how do we calculate that average? Well, we have to put in some limits. So for example, if we're interested in the average position of a particle over a range in our box between x equals 0 and x equals a, we're going to have an integral in here. And what we do is we sandwich the operator for that. Technically, this operator should be a capital. We're going to sandwich that operator in between the wave function and the complex conjugate of that wave function. We're going to operate on the regular wave function, not the complex conjugate. And with the assumption that the wave function is not normalized, we're going to include in here on the denominator in here effectively the wave function squared. We know that this denominator of course should be 1 in the event that the wave function is normalized. Okay, so here's our key expression. Where does it come from? Let's have a look. So we actually derive this with the following approach. So let's imagine our operator for position acting on our wave function, and what we care about right now is this average or expectation value for x. So we're going to write this into an expression, first of all, that mirrors the Schrodinger equation. And then what we're going to do is we're going to say, let's multiply both sides of this expression by the complex conjugate of the wave function, and then we're going to integrate over the limits that we care about. So the first part of this would be to multiply by the complex conjugate with respect to x. That is what sandwiches this operator in the middle in here. Leave yourself some space in here because we're going to add to this expression in a second. So now we're going to put in our complex conjugate in here, multiplied by the average value of x, which we don't know what that is yet. Okay, and next up we're going to take the integral of this over the limits that we're concerned about. So in this particular example, x equals 0 and x equals a, and so we integrate with respect to x. Same thing over on the left hand side. So whatever we do to one side of the equation, we have to do to the other side of the equation. Now of course what we recognize is that if this x in here is a constant, so it's a measurable number for its position or its average position, then we can pull that outside of the integral on the right hand side. So let's write that down as shown, and really that allows us to it's going to be a denominator shortly. Really, when we think about it, this expression is really our normalization condition, right? And that means this would be equal to 1. And on the left hand side, the integral stays the same. And so now it's fairly straightforward how we got this equation from the previous slide, because we're basically now going to rearrange this equation as shown, and we're going to divide by the probability for the normalized wave function. And that's how that expression is described. Problem B8 is a good problem that ties in with what we're doing in here. Let's have a brief look at that. So what we're trying to find in problem B8 is we're trying to find the average position, and we have a wave function that is now known to be 2 over a, it's to the half sine n pi x over a. There's a solution. So how would we calculate x in here? So what we're going to do, we're going to have 2 over a to the half sine n pi x over a multiplied by the position operator. So the position operator is simply x. Okay, so that's our position operator. It's simply x. So we looked that up in page 148 of your textbook. And so, by the way, on the left-hand side in here, this is the psi star, but it's not which is a complex conjugate, but there is no complex number in here. So it's simply the same function as we'd find on the other side of the operator. So again, what would we get in here? This would be to the half, and this would be sine n pi x over a, and that is, or with respect to x, we know, by the way, that with the denominator being normalized, so the denominator there, because this is a normalized wave function, this expression here will simply be equal to 1. And so the nice thing about that is we can kind of concern ourselves less with the denominator and actually think more about the numerator. So in this particular case, I'm just going to delete this but make a note in your notes as to why that's happening. So it's a normalized wave function in the denominator. So this expression now becomes, so what we're going to do is we're going to bring the 2 over a outside the integral, and we've got a and 0 in here as our limits. And now we are left with x sine squared n pi x over a dx. So it turns out that this ends up being a standard integral. We can solve this. So I'm not going to do that here, but problem B8 deals with that. So the answer there ends up being a squared over 4. So that is the integral. So then what this means is we have 2 over a multiplied by a squared over 4. And so the answer here ends up being a over 2. And that's for all quantum numbers n. And really what that means, what's the average position that we would find our particle? And if we just think about that particle in a box at the moment, here is our box length, right? So this is x equals 0 on the left hand side and x equals a on the right hand side. So the average position for that particle is going to be a over 2. Which is not really surprising when we think about the simplicity of the particular system that we're looking at. It's the average position is going to be in the middle. When we sum up all the positions that particle can take over all time, over all values of n, then the average position is indeed going to be a over 2. So let's take another look actually now at how we might calculate the average momentum for this particle, and what do we expect that to be. So average momentum over that whole range, and then we have our momentum operator in here. So something that this brings to light, and this is a point that I want to make in here, is that if psi of x is the true solution, then it represents all there is to know about the system. And really, that's the reason why we have to include this wave function in a description, or in our ability to calculate the average. So I'm going to try to sum that up by saying, hence, we can know this average value of p, or of course the average value of x. In this particular case, we have an interesting scenario, because in the prior case with position, it really didn't matter where the x was. Note here that the x was in the middle of the equation, but with the operator simply being multiplied by x, it didn't matter whether the x was in the middle of these two functions or on either side. In this particular case, of course, we've got an operator, p hat, that's equal to minus I h bar di by di x. So actually, again, we can justify this by going all the way back to the Schrodinger equation. And so for a particular wave function, for a particular n, okay, we end up going through the same process as I showed earlier, where we start with typical Schrodinger equation, so h hat operating on psi is equal to E operating on psi. Then what we end up doing is multiply by the complex conjugate on both sides, and then integrating with respect to dx. And then of course we recognize because the E is a constant, it can come outside the integral. So this is what has given us the expression that I'm now drawing down in here. And so that again is equal to, I'm just going to jump straight to the solution here, or the conclusion, if you will. So we're going to put this E sub n on the outside, and psi n of x psi n of x dx in the middle there. And again, because this integral in here, if it's normalized, this is going to be equal to 1, we end up with this being equal to E sub n. Okay, so basically from all of this we make an assumption in general terms that to determine the average, we sandwich that operator between the wave function and its complex conjugate. So what we're going to do is, let's write down again a general case for this in the next slide. So generally speaking, the average of any observable of interest is simply going to be equal to wave function for n, so taking into account that particular quantum number, this is a general case, multiplied by the operator after it's operated on the wave function. Okay, so there's that, with the assumption here that the wave function is normalized. So back to our particular case with momentum. So we're plugging this all in from momentum. Our average momentum is equal to, let's put our limits in as a and 0, and again in here we've got our function 2 over a to the half sine n pi x over a. First function. Now we've got our operator minus I h bar di by dx, and then we've got inside the next square brackets, again we've got 2 over a to the half sine n pi x over a. So what we're going to find, I'm actually going to leave that to you to figure out. This is problem 3.9 in the textbook. Of course, the derivative applied on the right hand side to that sine function will turn that into a cosine function. So we'll end up with a sine cosine function. And what we're going to do, or so actually in problem 3.9, it shows that this result ends up being 0. So it shows that when you go through the math, that the average momentum is equal to 0. So that also makes some sense, right? Because at some point we've got a particle moving to the right hand side with a certain momentum. It's going to bounce off the wall and come back in the other direction. Again, the momentum is going to cancel it out, right? So we've got a positive momentum in one direction and a negative momentum in the other direction. So overall, we do expect that the average momentum would be equal to 0. So I'm going to assign problem 3.19 and have a look at that, and we can go through that in class. So the key takeaway, this will end up being one of our quantum mechanical postulates, but we can calculate an average or an expectation value for a particular observable that we care about, and this is how we do it. But we have to know the wave function to begin with, and that wave function tells us everything we need to know about the system once it's been solved in the 5 rules that we put forward, and once it's normalized. So now we're going to switch gears and take a look at a particle in a 3-dimensional box, and we're going to look at some of the outcomes of that particular mathematics, and think about how indeed the Hamiltonian operator ends up being separable. Let's take a look. So this is one of the hardest lectures to give because I have to actually start drawing things on the page, but this is in association with section 3.9. and that's particle in a 3-dimensional box. And what we're going to do is we're going to label these axes, and let's use the convention in this particular case from the textbook. So we're going to have the y-axis in the horizontal direction, we're going to have the z-axis in the vertical direction, and we're going to have the x-axis in this case going back into the page. So the length of the box here is x equals a, and we've got a width of the box here which is equal to y equals b, and we're going to have a height of the box in here which is z equals c. And what we're going to say is we're going to set up our system very similarly to how we set up our particle in our 1-dimensional box, and we're going to say that that particle is in the box. So what this means is that anywhere outside of the box the potential is equal to infinity, and therefore 0 is less than equal to x, which is less than or equal to a. 0 is also less than or equal to y, which is less than or equal to b. And 0 is also less than or equal to z, which is less than or equal to c. And what we now need to do is actually consider the momentum and the energy for this particular system. So we think for each of these particular cases, let's pick, for example, let's pick the energy of the system in the y direction. That's based on the kinetic energy, because the potential energy we're going to say is 0 so long as that particle is in the box. But that's equal to p squared over 2m, and it's p sub y squared over 2m. And we go through the usual process, and we recognize that the operator that's going to be associated with e sub y, we might call this h hat y, is equal to minus h bar squared over 2m di squared by di y squared. So that's what we expect to be our this is h bar squared. That's what we might expect to be the contribution to the energy, because really when we think about this, we're going to have a momentum in the x direction, we're going to have a momentum in the y direction, and we're going to have a momentum in the z direction. And when we add up all those kinetic energies, what we're going to recognize, by the way, is we've got that's equal to px squared over 2m plus py squared over 2m plus pz squared over 2m. So now what we're going to end up finding is we're going to have a new quantum mechanical operator. So I think this is the energy of the system in a classical case, but for each of these energies we're going to end up with an expression that gets popped in. So what does that look like? Let's go to the next slide and see if I can clarify this. So what we're going to find is that our Hamiltonian operator for this is going to now be minus h bar squared over 2m, and we're kind of factorizing this now. So go through, think about the math in here. So we're going to end up with di squared over di x squared plus di squared over di y squared plus di squared over di z squared. So this is our Hamiltonian operator. We plug that into our Schrodinger equation, which, as we know, is h hat psi is equal to E times psi. And what do we get? We will end up getting minus h bar squared over 2m. And now we've got di squared psi over di x squared plus di squared psi over di y squared plus di squared psi over di z squared. And that's going to be equal to E multiplied by this psi. And in this particular case, we're also going to recognize, by the way, that psi is actually a function of x, y, and z. Okay, so more formally, I would probably include this so that but it is x, comma y, comma z. So this is x, y, z in here, so on and so forth. That makes it a bit of a mess, but at least it's in a different color. Okay, one thing that I want to point out to you right now, we'll stick with this color. I am going to define something called del squared. So this is called del squared, and it is also known as the Laplacian operator. So we are going to define this because it's going to be much easier to work in the shorthand. In fact, how would that be in shorthand? It would be minus h bar squared over 2m del squared psi of x, y, z. That would be equal to E times psi of x, y, z. So it's just a form of shorthand that allows us to stop having to write this thing out over and over and over again. So what are we now going to do? Well, we're going to do something that we used a lot in chapter 2, and it was this separation of variables approach, right? So if we have this function psi of x, y, and z, okay, what we can also recognize is that there is an x function there is a y function there, and there is a z function there. And so we're going to assume that psi can be broken down independently into these three functions, x, y, and z. And when we do that, what do we get? So we're going to get the following, right? Minus h bar squared over 2m. This is going to be occurring all the time. We would get y of y and z of y, z of z, now multiplied by d squared x over dx squared, now minus h bar squared over 2m, and that's going to be x of x and z of z, d squared y by dy squared minus h bar squared over 2m, and then we've got x of x, y of y, and d squared z of z by d z squared. So that is going to be on the left hand side, and we're going to say that that is equal to, down here, this is going to be equal to E times x of x, y of y, and z of z. Okay, now we're going to divide throughout by this piece, right? So we then end up simplifying minus h bar squared. This is exactly what we saw in chapter 2. So we're now going to have the 1 over x on the bottom, d squared x of x over dx squared minus h bar squared over 2m, 1 over y of y, d squared y of y by dy squared minus h bar squared over 2m 1 over z of z d squared z by dz squared. So that ends up being equal to E. So now the key here is that each of these functions, this is just a function only of x, right? And this is a function only of y, and so on. Function of z. So when we now put this together, we've got this constant on the right hand side, but it turns out that because all of these three particular pieces of the equation are independent of the others, then they may all equal some particular constant. So we're going to say that this piece is going to be equal to E sub x as a constant, this piece is going to be equal to E sub y as a constant, and this piece is going to be equal to E sub z as a constant. When we add those constants together, by the way, we're going to get E. Okay, so let's pick, let's say, the y equation. So the y equation now is minus h bar squared over 2m 1 over y d squared y by dy squared, and that's equal to E sub y. But it turns out now, if we look at this equation, each of these equations is the same more or less general equation as for the one-dimensional box that we looked at in previous sections. So the key here, so we can draw on our prior results. So what I've now done is rearranged this expression, and this is the expression that we might expect that looks very similar to our eigenvalue problem, the Schrödinger equation that we've seen in lecture 8. So as I've mentioned, we're going to draw on our prior results, and let's think about what a reasonable solution is going to be. So we can have a solution here. A function of y is equal to, we're going to call this a sub y, so this is the constant, a sine n y pi y over b, where the subscripts here denote that these are a specific quantum number, so the n sub y is a specific quantum number for the I direction, and a is a specific constant in the y direction. And we're also going to recognize here again, just like with prior solutions, n is equal to an integer 1, 2, 3, etc. So we can imagine now doing that for all of these, right? So we've got our y function, so all we have to do is go back to a prior slide and we look at this mess, and we say, you know, what do we have here? So here's this whole equation, the whole left-hand side of the equation, and we now kind of know what these functions are going to look like, right? So in fact, it's down here. We're going to sum these three up. So let's have a look, and that now ends up coming out to be. So we recognize now, of course, that psi of x, y, z is equal to x of x, y of y, z of z. So that ends up being equal to a x, a y, a z sine nx pi x over a sine ny pi y over b sine nz pi z over c. And so of course we also have to go through the process of normalizing this function, and so this starts to look a little bit more complicated, but it's really all the same thing that we've done before. The way we're going to start to write these, by the way, is as shown. So we're going to write the dx and the dy along with the integrals in here, and then we're going to follow with our complex conjugate of the wave function here, and the wave function itself, x, psi of x, y, and z, and that is equal to 1 because that particle is in the box. So after the normalization process, so we won't go through this again here, but we've seen how this normalization works. We're going to plug these functions in, and we're going to respectively integrate for each of those, sine n pi x term, the sine n y pi y term, etc. So I'm just going to provide in the next slide the solution that includes a normalization constant. Let's have a look. So this ends up being, the final solution ends up being equal to 8 over a, b, c in the denominator to the half, so it's the square root of that, sine nx pi x over a sine ny pi y over b sine nz pi z over c. By the way, this also shows up in problem 3.30 in the textbook. Okay, so I encourage you to take a look at that. We're also going to recognize, because now we've got a new energy, okay, and this energy is equal to h squared over 8m nx squared over a squared plus ny squared over b squared plus nz squared over c squared. And really, when you think about it, this kind of makes sense, because if we, for example, take the x terms, and we should be familiar with this at this point, so we're going to have something like h squared nx squared over 8ma squared. So if you think about it, this portion is just what we've seen. It's just a very similar situation to what we've seen for the particle in the one-dimensional box. So, why are we going through all this for this three-dimensional box? When do we get the lowest energy? Okay, so now we know that, of course, energy is a function of these quantum numbers, right? So it's a function of nx, ny, and nz. So what's the lowest energy? Well, the lowest energy is going to be when n sub x is equal to 1, n sub y is equal to 1, and n sub z is equal to 1. That's the lowest energy. Now, let's think about when we have a cube. It's a very special situation. So when we have a cube, then a equals b equals c. So the denominators in here are all the same. So that makes things a little easier for us in some respects. So the lowest energy, by the way, E111, is therefore going to be, this is when quantum number nx is 1, quantum number ny is 1, quantum number nz is 1. That's going to be therefore equal to 3h squared over 8m a squared. So the a squared there is equal to the b squared, is equal to the c squared. The next lowest energy, so the next energy state is actually going to be E211, which is equal to E121, which is equal to E112. And if we do the math in here, so we've got to put a square term of a square of 2 in here at some point. So it's going to be 2 squared is 4 plus 1 in here. So that gives us an energy of 6h squared over 8ma squared. And again, that's the situation where we have a cube where all the dimensions of that object, of that box, are the same. And what we're going to do is we're going to say there's something here called degeneracy. And what the particle in the three-dimensional cube does is it gives us an opportunity to introduce this topic called degeneracy. Degeneracy. And degeneracy occurs because of the symmetry introduced when the box is a cube. What is degeneracy? Degeneracy basically is when we have multiple energy levels that have different quantum numbers but all have the same energy, right? So if you think about it, what we've got in here, we've got an E111, and then we've got these three levels, these three states that all have the same energy. So this would be, we've got the E211 state here, the E121 state here, and the E112 state. And all these energies, they're different states, but they all share the same energy. And that is called degeneracy. So that's an important point in there. The interesting point here, another interesting point, is that the degeneracy is lifted when the symmetry is destroyed. So the last point, and this is from chapter 3, the last point from Macquarie. We're now coming to the end of chapter 3. The last point is the three-dimensional particle in a box problem reduces to 3 one-dimensional problems. That's what we've seen happen, right? So effectively we can solve this three-dimensional particle in a box problem by reducing it to, and through the separation of variables, these 3 one-dimensional problems. And I wrote earlier, I said that we might even think that the Hamiltonian operator in here, we've seen how this is done, is actually equal to 3 separate Hamiltonian operators, because we can sum up the energies for each of them, the kinetic energies in each of those directions. And the point here is that this is an illustration of the fact that the Hamiltonian operator is separable. What else? So this is consistent with the operators of quantum mechanics being linear. So Hamiltonian operator is separable is a key point, and also we're again reminded that quantum mechanical operators are linear. So that's it for chapter 3, and we're going to jump over now into chapter 4, and we're going to formalize some of these conjectures from chapter 3, some of these postulates, if you will. We're going to call them, fundamentally, we're going to call them quantum mechanical postulates. So let's have a look in the next section of the lecture.